Obrigado pela presença de vocês aqui. Prazer muito grande para a gente ter o Richard aqui, falar um pouquinho sobre ele. Richard Guia, da Universidade de Sydney, na Austrália, Departamento de Arquitetura. Lá ele tem o departamento do Laboratório de Qualidade de Ar e Terra, líder do conforto térmico. Tem uma pessoa que fez, inclusive, a dupla de formação aqui com a gente e lá com ele, Cristina Grande, que é coautora do trabalho que vai botar aqui, e hoje é professora lá na Universidade de Sydney. A gente tem uma colaboração bastante grande com ele. Eu estive lá no laboratório dele em 2012, fiz um trabalho sobre uma proposta de norma brasileira, conforto térmico. É interessante colocar para vocês que essa norma foi aceita pelo Comitê 55 da CP 55, da Brava, está revisando as normas de conforto de ar-condicionado, as 640, texto 2 sobre conforto térmico, e eles aceitaram a proposta que a gente apresentou, que é basicamente baseada muito no trabalho do Richard. Richard conseguiu, através de uma grande pesquisa com a Ashray, desenvolver um modelo adaptativo e botar ele dentro da norma americana. A norma americana de ar-condicionado usou um modelo adaptativo para um pouco contra a questão do ar-condicionado mais estático. Então foi uma revolução que ele conseguiu, junto com a Guia Braga, da Universidade de Berkeley. E Richard tem feito muitas pesquisas na área e ele vai relatar aqui para vocês um pouquinho sobre a questão mais do presidencial. Tem sido uma atenção muito interessante dele. Ele vai dar palestra em inglês. Né? Depois, se vocês tiverem perguntas, eu posso fazer intermediação, se vocês não conseguirem falar inglês, sem problemas. E se anotar alguma dúvida, de alguma parte, eu posso tentar não vai ser uma tradução. So, I said nice words.
Thank you very much, Roberto. and thank you very much for coming to this talk. I've been gently introduced into Brazilian culture in the last couple of weeks. Last week. Actually gently introduced, probably quite the right word for it, but it's been a great time. I've really enjoyed having a look at Brazil. But I keep on thinking it just looks like Australia. It really does just look like Australia. Then I scratch the surface and it's nothing like Australia. Anyway, thank you for coming on. So I think Roberto told you a little bit about my history, my Czech history, and I've been doing this stuff for probably too long now. I've been doing thermal comfort research for counting up 34 years, and sort of always scratching around looking for something new to say about thermal comfort. And many of my colleagues along the way have given up. They said, thermal comfort, it's all done, it's finished. We're working with Fanger, the father of thermal comfort research. That's back in the 1980s, way back then, when I was doing my postdoc with him, he said, thermal comfort is finished. I finished that topic. I wrote the book. There's nothing more you can say about it. But here we are, still, a couple of decades down the track, and we're still doing it. And so this is a talk that I've been shopping around the world. I've been presenting it in India. In December last year, I gave this talk in India to some colleagues, and now I'm in Brazil doing a tour. And the next stop on the tour, on what I call the Skull and Bones tour, is China. I'll be in Beijing in March through July, doing some work and related to this topic. So it's about residential thermal comfort. I think most of what you've learned and what you've heard about thermal comfort is about office buildings, and the residential sector is kind of, well, not forgotten, but it's just assumed that it's it's going to be the same as the office environment. So there's not much done in residential settings. So that's the basic topic. And the reason I'm sort of doing this, what I call a bricks, straw and bones tour, India, Brazil, China, but I won't go into Russia. The reason I'm doing these countries is that I think that the method that I've got here could easily be rolled out in all of those different contexts. I think it's going to be really interesting to compare India, Brazil, China, Australia. We have economies, cultures, and quite diverse, and this assumption that things are universal is maybe I'm not so convinced. So anyway, that's the broad background of the project. Now, Roberto's told me a little bit about the audience. I think I've got a mixture of architecture and engineering. And is there anybody outside those two disciplines? Okay, so I'm going to assume it's a 50-50 split between the architects and the engineers. I won't be putting any mathematics or equations on the board, but I'll just give you a quick overview of the history of thermal comfort and where this topic sort of fits into. So the topic of research, thermal comfort's been around probably 100 years, and really the landmark early papers go back to the beginnings of what we now know as ASHRAE, that had a laboratory in Philadelphia back in those days. And so ASHRAE came into being because Carrier invented commercial air conditioning, basically. It's now that. And the question was, how do we, what sort of temperatures do we need to create inside buildings for comfort? So it's got a long history, 100 years of history. But as I said earlier, the overwhelming majority of that research comes from commercial office buildings, because that was probably the most important application of air conditioning in terms of overall economic impact. I think the office setting was the first and foremost place to be fully air conditioned. But then, of course, we've seen air conditioning applied elsewhere. We've seen it in healthcare environments. We've seen it in schools, universities, educational environments. Vehicular patterns is another interesting domain of thermal comfort research. Apparently, the next stop on this is the Brazil leg of this tour. I'll be looking at laboratory mock-up of the aircraft cabin, where people do thermal comfort research. And then even outdoors and semi-outdoor environments have been the subject of thermal comfort research. And maybe straight outdoors is a bit rare, but semi-outdoors, sort of environments where you can partially control aspects of the thermal environment by air movement or creation of mist. Roberto was telling me about an application he saw recently, even in a humid context like in Brazil, where fine mist was injected into the atmosphere above the occupants in a semi-outdoor context. And by the time it descended very gently to the occupants, it had partially evaporated and, of course, reduced its temperature. We're still not using the noise from the air conditioning noise. So, semi-outdoors, it's another interesting application. But I think something that I've learned going from one context to another is that you can't assume that what is comfortable in one context is relevant and applicable in those other contexts. A lot of my colleagues make that leap of faith, and I have a bit of a disagreement with them about it. There are even people who think that the comfort definitions that we come up with for buildings, let's say office buildings,
can be applied in outdoor contexts, semi-outdoor contexts, which to me is just nonsense, absolute nonsense. So I call that like deterministic logic, and I hope you don't mind, Roberto, I suggest that the engineers are the perpetrators of deterministic thinking, often in this discussion. And they assume that we're just kind of like thermometers, that we're just comfort instruments, and if we put the instrument into any context, it will register a reading. And it'll be a correct and true reading, just like a thermometer. But the reality is it's not quite like that at all. There are contextual aspects to this topic, which I find fascinating. Anyway, so the bit that's missing in that list of contexts and settings is, of course, the residential setting. And it's interesting to wonder why we haven't seen so much work on residential settings. We spend an awful lot of our time in residential settings, so it's maybe a bit of a mystery as to why we haven't seen so much thermal comfort research in that setting. Why would we expect residential comfort to be different from, let's say, an office setting? And well, when you think about it, one of the defining characteristics of a residential setting is that the occupants have a high degree of adaptive opportunity. There's much more freedom to adjust the environment in a residential setting. Adjust an environment and also adjust the occupant to make themselves comfortable than would be in, let's say, an office environment or a vehicular environment. So that's the first reason for thinking that maybe residential might be different to office settings. Climate is another kind of obvious difference in residential settings. Here in Brazil, for example, in the last couple of days I've seen people very relaxed dress codes in their residences. Fairly relaxed actually in the workplace as well, but still it's sort of on a continuum, and there are these differences. Another reason for thinking that residential settings would be different would be the energy bill is being borne by the occupant directly in the residential context. In an office environment, it's not. The boss is paying for the energy bill. And so we might think that cognitive dimension could influence comfort. And then, of course, the activities that we're performing inside the building might be different in residential settings compared to office settings. Another reason why you probably haven't seen that much work on residential settings is that there's no need for a standard in a residential context. People are free to do to adjust their environment as they see fit. Whereas in an office environment, typically it's a shared space. You have multiple occupants in one system, so you're trying to find an optimum condition for many different people. Hence, the requirement for some like comfort standard. But in a residential setting, it's much more diverse, and maybe we don't need to worry so much about setting standards in that context. But having said that, there should still be strong interest in thermal comfort in residential settings, and there are strong policy drivers for attention to this research topic. And those policy drivers are pretty obvious. First and foremost, I think they refer to the greenhouse aspects of energy consumption in the residential sector. In Australia, for example, over the last 20 years, there's been a 40% growth in direct CO2 emissions in the residential sector. And for that reason, there are policies emerging that will affect thermal comfort in the residential sector. Another dimension of this problem is heat electricity demand. I suspect that Brazil is comparable to Australia in that the extreme peaks in electricity demand occur during heat waves. And when you dig deeper as to why, what's the connection to weather, the answer comes back, it's mainly residential air conditioning. And everybody with air conditioning turning the systems on at the same time and putting a very heavy burden on the grid. And the consequences of that are, well, it's not such an environmental problem, but it's certainly a resource problem in terms of money. The grid is constantly being upgraded at huge expense to cope with peak demand that occurs sort of maybe 5% of the time, 5% of the year. And so you've got that huge investment in infrastructure that's sitting idle for 95% of its life. And somebody's got to pay that bill. Somebody's got to pay the capital costs. So it comes back to the consumer. So there are all these sort of policy reasons that point to this topic as being deserving a bit more attention. And just to give you another illustration of why we should pay attention to this topic, this one's from the Australian context, and I think it's comparable to what I've seen in European countries as well. And it relates to a program that was initiated by the federal government in Australia to actually supply ceiling insulation to residences, virtually for free, just to improve the thermal performance of their residential building stock across the country. Why would the federal government be doing that? Well, the answer was, well, it was going to, according to the government's policy, improve our greenhouse gas emission performance. Australia's got the unenviable reputation of being one of the highest CO2 emitters per capita in the world. And the residential sector is deemed to be a key contributor to that unfortunate statistic. And so the federal government was thinking, if we improve the installation of households, we can cut back on energy and therefore reduce CO2 emissions. It was policy driven by what I call technocrats, who were applying what we call the deterministic comfort logic, the assumption that people would behave rationally and that if you that it all work in a mechanistic, deterministic way. To spell it out in Boolean logic, for the benefit of the engineers, the programmers, and the lawyers, the thinking behind the policy was like this, that if comfort stays constant and the house envelope, the thermal efficiency increases, then the electricity demand, including peak demand and greenhouse gas emissions, should reduce. That is the logic. But the householders, in the subsequent years that the policy was put into place, saw things a little bit differently. For them, the householders, the Boolean logic goes like this. If the housing envelope efficiency increases and the electricity demand stays static or remains constant, they can improve their comfort. They actually change or enhance their overall comfort. Rather than save energy, they'll spend the savings on comfort. And have you heard reference to the what we call the rebound effect? Energy economics. It's a familiar phenomenon. Behavioural economists have coined this term. It's basically summarising what I just told you there about the unfortunate Australian experience. The rebound effect is defined as the behavioural or other systemic responses to the introduction of new technologies that increase the efficiency of resource use. These behavioural responses tend to offset the beneficial effects of the new technology, and as a result of the rebound effect, actual electricity or greenhouse gas savings are significantly less than savings calculated by the technocrats using straight deterministic logic. So the calculations were all wrong because they forgot to take into account the fact that people behave kind of irrationally in this space. So I'll probably labour the point here why the residential sector is under-researched. Another kind of obvious reason is a practical one, and that it's extremely difficult in logistical terms to do this stuff in the residential context. Because it means, well, just by contrast, when we do a thermal comfort survey in an office building, we typically approach the owner of the building, or rather the tenant of the building, the employer of the occupants, get their permission to do the study. Once that permission is obtained, we move in with our equipment, and in a couple of days we can go through hundreds of questionnaires, get lots of data very, very quickly and efficiently. In the residential context, you can't do that. There's no single authority that you get permission from. You've got to get permission each and every time you knock on the door. Very tedious. So a lot of work to get data. So we've been looking at those logistical problems and trying to think of a more efficient way of doing it. There's got to be a better way. And indeed there is. And we've noticed here in Brazil, just like in Australia, and believe it or not, just like in China and just like in India, the smartphone revolution has taken hold well and truly. I don't know what the penetration rate is for the Brazil market, but it's probably getting close to saturation. And certainly in my country, virtually everyone's got a smartphone these days. So we think this is the magic solution to the problem of doing thermal comfort research in residences. It's an interactive device that gives excellent user experience. It's always on. That's one of the fantastic features of the smartphone in this research application. It's always on, and it's always with the owner. The owner takes that phone literally everywhere. They take it to the beach, they take it to the bathroom, they take it to the bedroom, they sleep with the phone. The phone goes absolutely everywhere. And so, in terms of success, it sounds a bit intrusive, but you have to think it's a great opportunity to actually get some feedback from people. So, smartphones, we think, present a direct, frictionless link between the researcher and the respondent in residential settings. So that's the way we're going. And one of my co-authors on this presentation, Tom Parkins, is my technical lead, sort of does all my computing stuff. He's a terrific programmer. And he's developed this little software environment for the development of questionnaires, comfort questionnaires. Have you heard of SurveyMonkey? SurveyMonkey is sort of a generic questionnaire application on the web. You can access it for free, and you can design questionnaires electronically and then send them out as an email. Well, we've kind of borrowed that concept, so we're calling it not SurveyMonkey, but Comfort Tube. And it's the same basic concept. We develop the questionnaire on this application, and then we distribute it not through the web, but rather through the 3G network to the respondents' handsets. In this application, if we're talking about, let's be honest, fairly intrusive surveys that will pop up on the respondent's phone any time between 8 a.m. and 10 p.m. So we're really kind of intruding. It was imperative that the questionnaire was really short, absolutely short, quick, snappy. And so, just to make that point, I've got a little demo here. The questionnaire as it appears on the smartphone. Text message arrives. The respondent clicks on the hyperlink in that phone, in that message. First question, are you at home? Next question, if you are at home, whereabouts in the home? Now, we get down to business. Thermal comfort, thermal sensation, slider control, feeling slightly cool. few questions about other adaptive opportunities that have been availed in that setting. Even a very, very simplified questionnaire on clothing, trying to get a ballpark estimate of clothes that is. And that's it. All over. And the duration of that survey was 1 minute. So that's the basic research design. We've got a sample of householders. They've got smartphones. We peppered them with these questionnaires. And that went for about 18 months. Not every day. We might have given them a break for a couple of days, maybe once a week. But then, under special weather circumstances that we were particularly interested in, like heat waves, we would pick them more frequently. And we had surprisingly good compliance. We were very, very, very pleased with the small attrition rate. We didn't lose many of the respondents across the 18-month period. They got very familiar with the questionnaire. They could do it probably faster than 60 seconds. And that was the key. They said they didn't mind because it was so quick. So in research design terms, it's what we would call a classic longitudinal design. We've got a relatively small sample. I think we had about 45 or 50 households in Sydney. And we repeat measure across a long period of time. The alternative research design, the one that is probably more familiar in office buildings, is what we call a cross-sectional design, where you have just one visit, but you have many, many, many respondents. So much, much larger sample size. Anyway, so this is longitudinal. And I've just described to you the subjective aspect of the data, the questionnaire data. But if you have read anything in thermal comfort research, you know that there's another side to the problem, and it's the objective environmental conditions. So the key concept in thermal comfort research is putting the subjective with the objective data and analysing the relationships. So on the objective side of the research problem, we've got some very, very cheap, simple, affordable, and durable temperature measuring devices called eye buttons. We discovered them we got onto them about 3 years ago. Our physiology department was using them to measure skin temperature. Terrific technique to measure skin temperature. But the eye button is, as you see, it's like a battery from a watch. It's about that size, or even smaller. And it measures at various resolutions. You can have it at 0.2 degree resolution, or you can have it at 0.5 degree resolution. You can have the higher resolution, but shorter duration of memory, or you can have the lower resolution and longer duration. So we chose the the coarser resolution and the longer memory. And we were measuring this thing in situ every 15 minutes. It would record a temperature, put it into its memory, and put a timestamp on it. And these devices retail about $25 each. So at that price, we can afford to buy literally hundreds of these things in the area. Terrific. So we put them in several rooms in the household, and we also put them into the air conditioning devices in the household as well. I'll explain why on the next slide. In an ideal world, if you were interested in knowing when the system is turned on, you would have sub-metering in the building. The problem with that is, of course, that you've got to have an electrician to do the installation, and then it gets very, very expensive. So we came up with a very rough and ready approximation, but surprisingly efficient, surprisingly effective. And it consisted of putting a temperature, an eye button, into the supply path, the air supply path of the air conditioning system, and another one in the occupied zone. Very simple. And so, applying a very simple algorithm to the data from those two temperatures, you can identify when the system is on. So, if the rate of temperature change in the air conditioning supply air is greater than some value, you know that the system was on. If the difference in temperature, the delta T, between the air conditioning unit and the occupied zone is positive, well then you know that the system is in heating mode. If the temperature difference is a negative, you know that it's in cool. So very, very simple, but effective, as I say. And with a 15-minute sampling interval on the eye buttons, we were getting fairly detailed temporal data on pattern of usage of the equipment within that sort of 15-minute accuracy. So that's the subjective data, the objective data, and also some contextual data about the household and the occupants. So when we went to install the eye buttons in the house, we asked a set of questions about the equipment that they've got in the house, something about the building physics of the house, the construction type, whether it's timber construction or double brick and what have you. Something about household demographics, the number of occupants. Something about household socioeconomics, income levels, education levels, etc. And as I said, something about the air conditioning equipment that they have installed. So, the Sydney results using this method, we had, in the end, a sample size of 45 households, which is, statistically speaking, it's acceptable. We would have liked a larger sample, but 45 is certainly a workable sample size. Within those 45 households, we had 220 years of temperature history from the eye buttons. 7.65 million data points, 7.65 million temperature readings on the eye buttons, 2,100 at-home questionnaire responses on the smartphones, so that's a good sample size. 4,900 air conditioning events, or instances where the equipment was turned on, and 11,800 hours of air conditioning use. What's that sample? So it's a big data set. Even though the sample size is relatively small, 45, massive amount of data, and we've only just squeezed it into an SQL database, which is why I'm able to now start pulling out sets. But to be honest, we've really just begun the analysis. We're just beginning. And it's interesting. It's very interesting. What we're finding. So I'll just show you some examples of the sort of results we can pull out of this database. The first one, you remember that very, very simple question on the clothing. We had 4 categories of clothing. We estimated those values, the flow values of those 4 samples or scenarios to be 0.2 flow, 0.4 flow, 0.6 flow, and 1 flow. So here's the distribution of those clothing values through the seasons. And not surprisingly, I suppose, you can see a very clear increase in the heavier 1 flow ensemble in the winter months, and of course an increase in the very light clothing values in the residential context, so during the summer months. Residential air conditioning events by month. An air conditioning event is simply an occasion when the equipment is turned on, and the distribution through the seasons is plotted here for you. The heating load is the red bars, and the cooling load is the blue bars. And again, not surprisingly, the cooling predominates in summer months, peaking in the January season, in the January month, and tapering off to virtually zero in April in the Sydney climate context. Around about April, we start to see heating events. That's the system working at reverse load. I don't know, is that common in Brazil as well? The equipment is sort of heating angle, heat pump. And peaking in July, as you might expect, and then tapering off. So the months of April and September being the least frequently used air conditioning months. Now here's something that was kind of interesting. We were surprised by these data, and that is the duration of the equipment being turned on. I assume people turn these things on and then left them on for sustained periods of time. And the data tells us something else completely. Most frequent events were short duration, less than an hour. So people are using the equipment just to take the edge off. Maybe coming home from the office, finding a very warm house, and then cooling it down with air machines. And then once the house is sort of a bit equilibrium, maybe reverting back to natural ventilation. So 1 hour was the most typical duration, especially for heating mode, but also for the cooling mode. Had a lot of air conditioning systems in bedrooms, and I would assume again that people would set the equipment running in their bedrooms and just wake up the next morning with the system still running. But in actual fact, durations of 7 to 8 hours were very infrequent. That people obviously are using a timer device on the equipment, using it to get to sleep, use the air conditioning to get to sleep, and once they're asleep, the system will automatically turn on. So these are interesting. These are new results. I don't recall seeing anybody sort of drilling down into the details of how people use this equipment in the residential context. The times that they're using the equipment were interesting as well. Cooling on the left-hand side and heating on the right-hand side. In both cases, heating and cooling, the period from 4 p.m. through to midnight was the most frequent for these heating and cooling events. But in the cooling mode, the next most frequent event was in the period between 10 a.m. and 4 p.m. Obviously tracking the cycle of temperatures outdoors. In the case of heating mode, though, the most frequent after the evening period, the most frequent occurrence was between 6 a.m. and 10 a.m. Fairly light usage between midnight and 6 a.m. in both heating and cooling modes. So one of the questions that we've been requested to investigate by the building simulation researchers is the trigger temperature. And I was having this discussion with Roberto just the other day about an annex in the International Energy Agency dealing with occupant behaviour. And just recognising how important occupant behaviour is on overall energy consumption in buildings. So the IEA is investigating occupant behaviour, and one of the big questions that they would want to know is what temperatures trigger the decision to turn on an air conditioning system? Because in the simulations, that's an assumed value, and the assumptions are based on various models of thermal comfort. So it's kind of interesting to see whether the models actually stack up against real occupant behaviour. I don't think anyone's done this before. So here's some data on that sort of question. We're looking at the temperature in the occupied zone of the room at the time, or I should say just before, the air conditioning system was turned on. So we can identify when the system was turned on, and then step back 15 minutes and look at the temperature from the occupied zone at that point in time. And we're calling it the trigger temperature. And the distribution of trigger temperatures in Sydney in the summer, in cooling mode, shows a very prominent peak in the range of 26 to 28 degrees, which is probably a little bit higher than the modelers would assume. I don't know, what do you think about it? My discussions with people who do energy plus simulations have indicated that they assume that people turning systems on around about 24 to 25 degrees. degrees Celsius, whereas in Sydney the most common trigger temperature was 27 or 28. Or sorry, 26 to 28. And we think, on the basis of other literature, that temperature, that band of temperature in Sydney corresponds to the threshold of sweat for people who are lightly dressed with low metabolic rate, almost sedentary. The trigger for sweating is going to happen somewhere in that range of 26 to 28 degrees Celsius in a climate like Sydney's. It'd be really interesting to look at what that trigger temperature is going to be in Brazil, for example, or India. So that's interesting. In the case of the heating decisions, the trigger temperatures for turning on the heat pump in heating mode in wintertime, it's not as clear cut. There appears to be no, it's not as pronounced trigger temperature. The distribution is more, it's flatter. But the most common trigger temperature appears to be in the range of 16 to 18 degrees Celsius. It's a very complicated graph that I'm going to skip over for this talk, and just go straight to these next graphs on trigger temperatures. It's interesting to look at the trigger temperatures at different times of the day, and the trigger temperatures for cooling, that is the temperature of the occupied zone at the point in time when the air conditioning was switched into cooling mode in the daytime, 10 a.m. to 4 p.m, and the night time from 4 p.m. through to midnight. And the distributions are more or less the same. So it would appear as though the trigger temperature for cooling is pretty well constant, regardless of time of day. Heating is a different story. The trigger temperatures for heating show quite different distributions depending on time of day. So the morning in this graph refers to the period between 6 a.m. and 10 a.m, and the evening or the night refers to the period between 4 p.m. and midnight. And as you see, the 4 p.m. to midnight data show a pronounced peak around about 16 to 18 degree range in the night time. In the daytime, or rather in the morning, it's actually it's flattened out, and it seems like people are turning the equipment on because they wake up, basically, regardless of the temperature. Bedroom temperatures. We know nothing about bedroom temperatures. It's amazing how little data there is on bedroom temperatures. And it's a great topic. It's a terrific topic. I've heard of stories from my colleagues in Singapore, anecdotes, but not research, anecdotes that people in Singapore use feather eider towels on their heads. Now, Singapore is a very hot, humid, equatorial climate. The latitude is 1 degree north of the equator. It's much more humid than this. And people are sleeping under eider towels in their bedrooms because they've got aircon. And they crank the aircon, push it down to 18 degrees Celsius, and they get a very nice, deep sleep. So, but very little data on this, and it's kind of interesting to I think we've now got a way of investigating comfort in the bedroom. So here are some snippets from the Sydney bedrooms. We're looking at average bedroom temperatures at night time from 10 p.m. through to 7 a.m. Unfortunately, we don't get questionnaire data. That's the downside, but we've got the iPhone data. And we also know something about the air conditioning, how it's being used. And in the case of air conditioning, in the cooling mode, you can quite clearly identify a range of bedroom temperatures between 22 and 24 degrees Celsius. That's in the later summer months. In the early summer months, it's a little bit higher. just a little bit, and it's between 24 and 25 degrees from October through to December. But not a huge difference between bedroom temperatures with air conditioning and without air conditioning. So people are using the air conditioning in Sydney, it seems, fairly rational, using it to keep a fairly stable room temperature. Now, looking at living rooms, looking at the distribution of living room temperatures during the daytime from 7 a.m. to 10 p.m. with air conditioning and without air conditioning. The difference is negligible in the summer months. So it would appear as though people are rationally behaving. They're using natural ventilation when it's appropriate, and switching on the air conditioning to bring it back to those sort of temperatures that they found comfortable when the external environmental conditions were not so convenient, not so comfortable. There's a discrepancy between air conditioning mode temperatures and non-air conditioning mode temperatures in the winter months, and we attribute that the air conditioning mode is obviously that they're using it in reverse cycle mode. Now, the next graph is kind of one of the more mysterious aspects of the data that we've found so far. And if I can just recap what I was referring to earlier in this talk is the deterministic theory or deterministic logic of thermal comfort. That is that we have a physical environment that elicits a physiological response, and the physiological response elicits a state of mind of comfort or discomfort, and that state of discomfort or comfort elicits a behavioural response. So we go through this sequence of the cause and effect in this deterministic model. That's the assumption. And you could probably say it's fairly evident in the data we got here from living rooms on thermal sensation. So we've got the thermal sensation scale on the y-axis. We're just looking at the warm side of the scale because that's all we've got in summertime. And we're looking at temperatures 23 to 24 up to 28 to 29. And we're looking at the average thermal sensation in the living rooms when the air conditioning is on and when the air conditioning is off in those different temperature periods. And there's some, anyway, looking at the data from the naturally ventilated scenarios, we see that thermal sensations are close to neutral at 23 to 24, and they rise gradually, on average, as we go into warmer temperatures, as you might expect. They never get above slightly warm, which would suggest that people are adapting in some ways to make sure that they can keep things within the acceptable range. But overall, I'd say that it's broadly following that deterministic logic: environment, physiology, comfort, and then behaviour. But what's interesting is that logic breaks down when the air conditioning is on. And we've got, for example, scenarios here in living rooms where the temperature is 23 to 24 degrees Celsius, the same as it was in the air conditioning case, but people were registering a much higher thermal sensation. And surprisingly, and that was the case of 24 to 25, it's on average 1.0, which is quite high. And it continues to rise fairly dramatically, up to 25 to 26 degrees Celsius. The numbers that I'm pointing at here refer to the sample sizes of these data. So the sample sizes aren't huge, but they're enough, I think, to make some interesting observations. And the observation that I'm coming up with here is that there's this discrepancy. Why do people feel warmer when the air conditioning is on than they do at the same temperature when the air conditioning is off? It's paradox. Various hypotheses as to what's going on there, but one might be that the logic is going in reverse, that people behave first, and then they adjust their thermal sensation to justify the behaviour. And we've kind of heard this, we have heard this in our surveys of thermal comfort, that it's what psychologists refer to as cognitive dissonance, that people adjust their perceptions and their attitudes to fit their behaviour rather than the other way around. And I think we're actually witnessing what could be called a bit of cognitive dissonance here in Australia anyway. So, it brings me to some very general conclusions. And the first and obvious one would have to be that the context matters, that what we've learned about thermal comfort in office buildings doesn't work directly in a residential setting. Which is a little bit disappointing in many ways because, the adaptive model of thermal comfort was based exclusively on office, or let's say 95% on office data. And yet we use that adaptive model in all sorts of contexts. We just assume that it's going to be the same in residential, in educational, in vehicular. We make a leap of faith. Well, what we're looking at here would suggest that leap of faith is maybe not quite justified. So that's the first general conclusion. Second one, something I've always known, and that is that comfort is not deterministic. It's much more complicated than that. This logic, physics, physiology, psychology, behaviour, not so convinced. Another conclusion is that residential air conditioning usage patterns are not 100% rational. So our colleagues in the thermal simulation research field should do a little bit more work on the behavioural side. I think the International Energy Agency's Annex 66 is a very good one. It's going to be a very useful exercise to get more real behavioural data into simulations. Implications of this sort of research for peak electricity demand. I think you've all heard of time of use tariffs. When we talk about smart metering on residential electricity supplies, we have the opportunity to charge the consumer according to the costs of electricity production at the time that they're using electricity, which is sensible, rational. Setting a price signal and assuming the price signal will adjust will impact the behaviour. Well, it's a crazy idea, but I just thought with the technology that we've just been talking about here, you can actually start charging according to the frivolity of the decision to use air conditioning. Using air conditioning when the actual ambient conditions are 23 or 24 degrees Celsius would seem to be pretty stupid, so they're the ones that should pay. And as I was sort of alluding to in the introductory comments about this work, Australia is an economy, it's a developed economy with lots of cheap energy, rapidly rising air conditioning penetration rates in the residential sector. I think we're sitting at about 60 to 70% now, and excessively high greenhouse gas emissions. What about our countries? What about other economies? So, hence the interest in the BRICS. Very interested to explore China, India, and hopefully we can find some collaboration here in Brazil. The research methods we've just been describing to you absolutely turnkey. You can find them anywhere in the world. The smartphone questionnaire is, we can operate it from anywhere in the world to any phone in the world. And the costs of the calls, we buy batches of SMS call fees. It costs us about 3 or 4 cents at each SMS. So it's affordable. We can run it virtually anywhere in the world. So that brings me to my conclusion. Slightly weird slide to finish on, but it's a camel ruminant. So you're ruminating now, thinking about what I'm going to be talking about. But perhaps you've got some questions.
Quiser fazer a pergunta em português, eu posso.
Quando eu visitei o laboratório dele, tinha alguns experimentos com ventiladores. Eu queria saber se foi feito algum estudo em relação, parecido com esse, em relação àqueles ventiladores, e não só aqueles.
When she has been to visit your lab, she visited Christina, and she seen some experiments with fans. They've done anything with fans also, with ventral settings?
Interesting question. I don't know the meeting it. Did you meet me when you visited the lab?
No.
Somewhere in India. Yeah, fans are interesting. I noticed they're very popular in Brazil. They're probably less popular in Australia. The air conditioning equipment is just so cheap, and electricity is so cheap that people just go straight for the air conditioning, which is unfortunate. But they do provide an interesting and much more energy efficient solution to cover. We haven't done any field work specifically on the topic, but you probably noticed in our smartphone questionnaire, towards the end of it, there was a question about other adaptive opportunities that had been used at the time that the questionnaire was being filled in. Any windows open, any fans being used. So the potential is there that we could pull out those fan usage cases and do some analysis.
She has probably seen these very fancy fans that don't have blades.
Oh, yeah.
And they're quite inefficient.
They use the guys and withdraw this sponsorship. But they're very inefficient. They consume a lot of energy and they don't have much energy.
Vocês já viram um ventilador que tem buraco assim, não tem espaço? Basicamente é um ventilador embaixo que distribui o vento pela lateral assim e sai por uma fresta. Extremamente
A question about you have some feedback for people that use the comfort chip. Because I introduce all my information for the researchers, but the researchers keep some information for feedback for me, like this or energy safe or something. Just some information for feedback for the research that I was introduced to the research, but the researchers have something for me at the end of the research or not.
You're talking about the householders?
Yeah.
Yeah, we I don't know, do you have ethics committees here?
Yeah.
Are they as much fun here as they are in Australia? They're a nightmare. They make us jump through hoops, ridiculous hoops. But anyway, one of the hoops is that we do what we're talking about. We have to give some feedback to the households. And so we did. We gave them, nice little graphs showing temperatures in their house. Just enough to keep everybody happy. We actually had very, very good cooperative households. We were impressed at how cooperative they were, because we were, I won't say pestering them, but we were there for 18 months, especially every couple of days, and they just happily did it.
The thing is trying to ask you is that if you can give some feedback to change behavior.
Yeah.
But this is not the intention of your thing. So it's a bit. It's a combination with practice. You will feedback to change behavior.
That's an interesting thing. That is a very interesting thing. We've got a few projects, all sorts of projects running at the moment, but the idea of feeding real-time comfort data into the control loop of the building, is that what we're referring to? That's where we're going. That's exactly the direction.
Thank you.
Next to this question, we started the talk saying that some energy efficiency strategies they don't work in the residential sector because they will start using use the same amount of energy but with more comfort. So how would be or which strategy could work would be like feedback?
That's a very good question as well. I probably oversimplified the rebound effect. In different parts of the literature, they estimate what it is, what percentage of the rebound effect is. So if you think of the amount of energy saved theoretically by improving the envelope efficiency as 100%, and the rebound effect is it varies in different situations. It could be 30%. So you say sometimes you save some energy, but not nearly as much as the deterministic logic would have you believe. So the calculations in the Australian context that we use to justify that program of putting free ceiling insulation in homes at taxpayers' expense. The calculations were quite wrong. I don't know exactly what the rebound figure was, but it was fairly significant. And so what's the strategy, what's the solution to that? It's a very good question. I think it's a research question. It's a research address. It's a very, very good question. I know there's a lot of stuff on the rebound effect in residential settings. People doing a lot of work up there.
Since the 70s.
Since the 70s, yeah. First, the name comes to mind, Kevin Roberts. Is that a question that would be of interest to your research?
I have one question. One of the things that you showed here was this very short fuse of air cons in dormitories. I mean, it's puzzling. And it could be an interpretation related, because the aircon in 1 hour can bring the comfort temperature that switches off. And it's like a fan. I don't know if the fan, you can pick the fan with your hand. So, could be on.
So you're thinking the compressor would actually be...
compressor is off, but the fan...
That's a very good point.
Because people will not wake up to that stuff.
No. The equipment would have a pretty smart control that would have a time setting.
Yeah.
That's possibly what we observed, and it's something that we can explore. But you remember one of the slides showed the algorithm that we were using to decide when the equipment was on or off. And there's this parameter called X. It was a number, basically, that if the temperature difference between there and there was bigger than X, we decided the equipment was on, and if it was less than this, it was off. So when the compressor side is off, that delta X, the delta T, would fall, do you think it would fall below the threshold of X?
You have to study what's this, the thermostat settings of the, but it might be not sufficient to be seen by your algorithm.
At the moment, the analysis is done very, very simplistically in spreadsheets.
Yeah.
But what you're referring to should be visible in the time series of changes.
Yeah.
So we could actually get a smarter algorithm just to double check on what that's what we're doing. Thank you.
No questions? Please.
Well, do you believe that if you adopt a time-dependent residential tariff, would the tariff allow people and also household people use preheat or pretty cool. After or before the peak hours, usually behavior could happen.
I think that behaviour will almost certainly happen. And have you heard of the product from Google called Nest?
No.
See, I was surprised to learn just last year that Google, of all companies, has gotten into home automation area. I thought they were information technology. No. They're now selling a product called Nest that is a smart thermostat. It costs, I think, about $150, less than $200. You can apply it to virtually any energy equipment in the residential sort of context. Very easy to install, and it's part of the Internet of Things. And it's connected to weather forecasts, and it's connected to, it learns through a neural network algorithm what the behaviour of the occupants are. It learns what their preferred temperatures are and when they come and when they go, and it can start to anticipate things. And I think in the not too distant future, it will also be aware of the cost of electricity and the time of that cost. And it will be making decisions, strategic decisions, just like the ones that you described. So if it knows that a peak event is coming, it will pre-cool the house. Hopefully the house has got enough thermal mass to store the heat for the heating and save on those tariffs. I won't save on greenhouse gas emissions, but it'll save money. Yeah.
The other thing on Nest is that it's based on the iPod dial. So that is percent.
So, interesting, Google getting into the house. What are they doing? And the answer would have to be they want to know. They want to know something about us. This is another way. I just want to know everything about us, everything about our lives, where we start. Massive amounts of part of how we use and the commercial opportunities. I heard somebody describe Nest as a crazy technology that will, when your house is burning down, you'll get an SMS saying, fire extinguishers are available.
Thank you for the presentation. Thank you for listening. It's interesting to see your bedroom and living room graphics saying that the temperature of the occupants are deciding the temperature they want their inside indoors, which is something very different that we use in simulation. We always used to say one temperature for 1 year, maybe a little data and something coming to the office. It's not what we see here is very different. So the question is, do you have any intuition? Because I think it's not simple, but do you have any intuition of why the occupants are deciding to put the temperature in summer, say 26 or 27 or 24? Is it the bill? Is it the weather? Is it maybe a health issue? Or they don't want to have a thermal shock inside? Why are they choosing that temperatures?
The short answer. Have you heard of the adaptive model? The adaptive model of companies?
Yes.
Well, that's basically what it's saying. That people, obviously they're dressing differently in different settings. So the same level of comfort can be achieved at different temperatures simply by varying the flow values. So I think that might be part of it. I think air movement in naturally ventilated premises is another strategy or another potential explanation for higher comfort temperatures in that residential setting. That's the first explanation that comes to mind. Have you got some hypotheses?
Also Roman? Soll die Roman?
About the people who were interviewed, did they have a similar profile, like economic goals and many hours? Did that matter to choose who was being interviewed, or did it matter?
That's a very good question as well. It's a pretty diverse sample. I would have to say it's not my statistical colleagues shut up when I say this, but I have to confess it's not a random sample. It was not a simple task to recruit that sample. You can imagine, by the way, can we send you these for the next 18 months? So in some ways it might be slightly self-selected, to use that term. But within the sample of 45 households, we actually did get a reasonable cross-section of Sydney humanities. To be honest, we haven't analysed the data according to the demographic data and socio-economic variables, and that's coming. That's going to be interesting. In a perfect world, we would have a much larger sample. I think 100 would be much better than 45. And in Brazil, if we were to do it here, I would be pushing for a bigger sample so that we could do exactly what you're referring to. Like one of the very interesting questions that pops up all the time when we talk about time of use tariffs on air conditioning equipment is that it's a socially unfair strategy because it means that wealthy people can turn down their home whenever they want. And people at a lower income bracket maybe suffer discomfort and simply because they can't afford the energy. And take it to its extreme, you might recall from the literature the term fuel poverty. In England, fuel poverty was a big issue due to that term from England, where old people die in their homes in England because they can't afford the energy to heat their houses. So we're not anywhere near that stage in Australia, but still there are these equity dimensions to the problem. It'd be great to explore them with the bigger sample.
Muito obrigado pela presença de vocês. Vamos agradecer ao Richard mais uma vez.